Recording in progress.
Okay, so I think it's recording now. Give me 1 second. Share. Yes. Sorry. Okay. I'll share my screen. All right, can you see the slide here? Great.
Yeah.
Okay. So today the agenda is I'll introduce you to the biostatistics unit here at Bouvet College of Health Sciences. I just wanted to share more about the resources that we offer through the biostatistics unit. And then we will talk about what is power, the application of statistical power analyses, the certain language of statistical power analyses that you will look at in GPower, which you'll be encountering, and then what is effect size, the factors that affect sample size, and the steps to perform a statistical power analysis. And lastly, we'll have some examples. We'll calculate sample size and effect size using GPower. So I gave my introduction, but I'll introduce again now that we're recording. My name is Neha Singh. I'm a biostatistician here at Bouvet College of Health Sciences at the Biostatistics Unit. I'm also a second-year PhD student in population health. In the biostatistics unit, I offer services such as providing assistance on study design support or creating a statistical analysis plan, a short blurb for the initial phases of the research project. I also provide assistance on sample size calculation or power analysis. And then towards the phase 2 of the research project, I provide assistance on performing statistical analysis based off of the research question of interest, helping out with data management, for example, data cleaning, handling missing data, and then performing data visualization. So if you want to create plots or figures or tables, I provide assistance on that. And then lastly, I also provide assistance on manuscript reporting, so providing interpretation of the statistical results and writing that in the methods and results section for your manuscript, and then addressing reviewers' comments or feedbacks. And then now we are also offering education and training. So I will be holding in the next couple of months, I will be holding a few more sessions where we will learn about how to perform data management or basic statistical analysis using SAS or RStudio. So please feel free to join those seminars as well. Lastly, we also offer virtual office hours every Monday and Wednesday from 1 p.m. to 2 p.m. This is a time if you're looking to, if you have a quick question, a 10-minute question that you'd like to address and you don't need a full hour consultation, feel free to join those virtual office hours. I can address your questions in those 10 minutes or see if we really need to meet for an additional 1 hour session. If you require any statistical support for your grant proposals or any research-related project that you're currently working on, feel free to submit a consultation intake request form. It is provided through the centralized intake form via the link on, it's on the centralized intake form app, and you have to select Biostatistics Core. It is also under my email, so once I send you this PowerPoint or the recording, under my email, there's a link to provide submitting a consultation intake request form. All right, so we'll get a head start. Let me see. 1 second, just make sure that, okay. Okay, so we will get a head start. Okay, so the first question, most important question that researchers have is how many subjects should they recruit in the study that will help answer their research hypothesis question? When you're working on a research project, the first question in mind is, what should be your population sample size that will be generalizable? So there are certain factors that affect in addressing for sample size calculation. First and foremost, there are a few things that you consider. What is the purpose of the study? Is it important to achieve both clinical and statistical significance? There's a difference because we usually tend to look at the p-value to identify statistical significance, but however, if there's a large sample size, we sometimes tend to receive statistical significance, but that doesn't mean that it's clinically meaningful. So there's an importance to identify both clinical and statistical significance. The second factor is population size. We want to make sure that our sample represents the target population. And so the target population that we're interested in, we want to make sure that our sample can be generalizable towards that target population. Third factor is the precision level or the margin of error, the precision needed to make a population estimate from a sample. So for example, how much higher or lower than the population mean am I willing to let our sample mean fall within a range? And then confidence level, how confident are we that the actual mean falls within our margin of error? And then lastly is the degree of variability or standard deviation. How much variation do we expect in our results? Is there a lot of variability between two samples of data, for example? So we're looking at, how much variability is that in our results. These are a few factors that affect sample size. So starting from beginning, what is power? Power is the ability of a statistical test to detect a relationship or a difference. The probability that a statistical test will reject a false null hypothesis. So in layman terminology, it is pretty much the probability of detecting an effect given that the effect is really there. If you see here, power, this is the formula for power. Power is equal to 1 minus beta, where beta is equal to type 2 error. Type 2 error is called a false negative because it is the probability of not claiming an effect when in fact it is there. So for example, a false negative would be that you did not have COVID, but you tested positive for it. Whereas type 1 error is probability of claiming an effect which is not there, and it is called a false positive. So these are the few factors that are very essential in performing your power analysis: the type 1 error, the type 2 error, and p-value, effect size. P-value, on the other hand, is the probability that you would obtain the effect observed in your sample or larger if the null hypothesis is true for the population. So the lower power is caused due to a lower sample size. Basically, when we're looking at power, we are saying that can we see that there is a difference, or can we see that there's a relationship based on our sample because it actually exists in a population? Do we have enough power to find that in the first place? Usually an acceptable power is about 0.80 or higher. However, some researchers usually do use 0.7 if they need a little bit more wiggle room, because there's so many other factors that go into the environment of education. And power analysis is usually performed a priori, so usually at the beginning of the study starts, because you want to make sure that you have enough power to detect significance before the study starts. Here you can see how type 1 error, type 2 error, and power relate. So for example, if the null hypothesis is true and your test does not reject the null hypothesis, then you made a correct decision. But if your null hypothesis is true, which means that there is no difference, and you reject the null hypothesis, you made a type 1 error, which was a false positive. Same, if the null hypothesis is false and the test does not reject it, you made a type 2 error, which was a false negative. And then if the null hypothesis was false, but you rejected the test, you made a correct decision. So this is how power, type 1 error, and type 2 error are, related to each other. What's more important also here in power analysis is understanding effect size. What is effect size? Effect size, it measures the strength of a phenomenon. So it's the quantitative measure of the difference between two groups of relationship between variables, independent of the sample size. So for example, if you look at this little plot, I tried to be a little fancy, but if you look at this little plot here, this graph, you can see that let's say the blue graph here is the null hypothesis, and the pink/purple bar is the alternative hypothesis. We are trying to see whether there is a significant difference between the null and the alternative hypothesis. And D here is Cohen's D, the effect size, which measures how large or how significantly different is the null hypothesis from the alternative hypothesis. So pretty much in effect size, we're trying to see if there's a difference between these two. How strong is that? And this comes down to different kinds of hypotheses. So for example, if there's different ways of there's different effect sizes based off of different kind of analysis that you're running. For example, if you're looking to see the relationship between two variables, then you're looking at R, which is the R is the relationship that provides the strength between two variables, and these are the Cohen's effect. These are the effect sizes. A small effect size with for correlation R is 0.10. A medium effect size is 0.30. A large effect size is 0.50. In regression, if you're looking at regression, then you will be looking at the regression coefficient betas. So you'll be comparing the beta estimates, coefficient estimates, and looking at your regression model and comparing beta 1 to beta 2, beta 3. So for example, if beta 1 is larger than beta 2, then you know that beta 1 will have more influence on the overall equation when you actually do the math, so that it will be a stronger effect than the other one. And in the mean difference in t-tests, you usually use Cohen's D effect size because it tells you the difference between the two, the blue and the purple line. In ANOVA, we use eta squared, which is the effect size measure. So for a small effect size eta squared ANOVA model, you're looking at 0.01 as a small effect size, medium effect size is 0.06, and 0.14 is the large effect size. These are pretty much the different types of effect sizes when based off of the different type of statistical tests you're running. So the most important thing to understand here is that when you are performing a power analysis, the statistical test is very important to direct you to the right way to perform power analysis. So just a note here, the larger the effect size, there will be a stronger relationship between the two variables. If the effect size is small to medium, that means that you will need to enroll more subjects to find a significant result. And if the effect size is large, you do not need as many subjects. Here's the application of statistical power analysis. So first and foremost, a step is to specify a hypothesis test. So it's pretty much based off of your research question of interest, your hypothesis test, which is using statistic to determine the probability that a given hypothesis is true. It can be either a one-tailed, which is one direction, or two-tailed, it could be going towards both direction. Usually a one-tailed test is more powerful than a two-tailed test because you're not considering an effect in the opposite direction. And then the next step is to determine the type of experimental design. So here you're looking at whether you're allocating treatments into different conditions or into a control or treatment group, whether there's a between subject, within subject design, whether there's matched pairs. So are you performing, is there a pre and post analysis that you're performing? Are you looking to compare two independent samples? The application of statistical power analysis depends on the kind of statistical design that the type of statistical design and your hypotheses of interest, mainly. Then the next step would be to determine the statistical power level and significance level. So usually recommended power level is 80% to 90% with a significance level stating of 0.05. And if you want a bit more wiggle room, then you can increase it to like 0.10. But the usual significance level is 0.05. And then effect size. What's the clinically meaningful effect size with estimate of variability? So effect size is usually determined either by prior literature review or by prior knowledge. And then if the effect size is not there, if there hasn't been any research study performed before, it's a pilot study, then you estimate to assume what would be the effect size based off of clinical relevance. So I wanted to kind of give you guys an overview of the language of statistical power analysis because when you look at GPower, and I will show you when we open GPower software, there's a few different options when you're running the statistical power analysis in GPower. The first and foremost is a priori analysis, which allows you to calculate sample size, given that you have information about the significance level, the power, and the effect size. When you're performing a post hoc analysis, it's usually if you want to analyze if you already have enough sample size or you have an idea of how much sample size you have and you want to calculate the power. So here you have the significance level information, you have the sample size information, and then you also have the effect size information, and you want to know how much power would it be to have that much sample size with this effect size that determines the significant difference in the relationship. The criterion option allows you to calculate the alpha, the significance level, given that you have information on the power, the sample size, and the effect size. And sensitivity, it allows you to calculate the effect size, given that you have information on the significance level, power, and the sample size. These are helpful because sometimes we don't have information on, we have information on the sample size, but we don't have information on the effect size. So we have a general estimate of how much sample size we can obtain in our study. We'd like to see what would be, a small or a moderate, medium, or a large significant difference based off of, or a relationship based off of a research question of interest. So it allows us to calculate the effect size. And then for the a priori, it gives us, based off of prior literature review or clinical relationship or clinical meaningful significance, that this is your effect size and you want to know how much samples should be enrolled into the study. So you use the a priori. We usually use the a priori or sensitivity mostly, but these two other options are also available if you have the rest of the information. So the factors that affect sample size. This will be a lot to take in, and hopefully it'll work. As your sample size increases, your power increases. It pretty much increases the precision of the results because a large sample size, it constricts the distribution of your test statistic. This means that the standard error of the distribution is reduced and the acceptance region is reduced, which increases the level of the power. The other factor is that sample size increases as the significance level decreases. So for example, a study with alpha of 0.01 requires more subjects when it's compared to a study with alpha of 0.05. Sample size increases as the variance decreases. So there's an inverse relationship between sample size and the standard error. So as we increase our sample size, our variability of the sampling distribution also decreases. And then lastly, sample size increases as our effect size decreases. As sample size increases, the variance of the sampling distribution decreases. And then if the distribution is more narrower, then there will be less overlap between the two sampling distributions, which results in a few type 2 errors. So less false negative errors, and it gives us great statistical power. So as our sample size increases, we have a smaller effect size. And then our p-value is based on the standard error. So as the sample size increases, the p-value decreases if the mean and standard deviation do not change. So here are the few steps to conduct a statistical power analysis, and then I can walk over with the examples right after this. The first and foremost step is to select the type of power analysis you will be performing. So whether it's a priori, a post hoc, a criterion, a sensitivity, it is based on the information that you have already in, from prior literature review, or that, you have made an assumption based off of your clinical relevance. And then select the expected study design that matches your hypotheses of interest. So whether it's a t-test or whether it's an ANOVA, whether you're performing a regression analysis, whether it's two-way ANOVA, if it's a parametric or a non-parametric test. And then perform it in GPower. So in GPower, at least there's a good thing where you are allowed to provide 3 of the 4 parameters. The usual, I set my alpha to 0.05 with a power of 80%, and the expected effect size will be supported based off of pilot data or literature review. And then solve for the remaining parameters. Okay, so here's the link to download GPower. It's freely accessible. There is a GPower guided manual online, which also gives you examples to look at for each test, statistical test, and how to perform power analysis using that GPower guided manual. But I will also walk you through some basic statistical tests to kind of give you an overview on how to run the power analysis using GPower. Okay, so I am going to see, I'm going to try to see if there is a way to side by side run this, and then hopefully it works. Sorry. Oh my goodness. Okay. Can you see my screen? Can you see both? Can you see both the?
I can't.
Okay,
Just
Yes,
slow down. Yeah, I think GPower.
do you see GPower on one side and then the PowerPoint on the other side?
Yeah, they're overlapping.
Okay, I'll just fix that right now, but I'll send the link to download in the chat. Give me 1 second. Did that work? Okay. I'll also show you. So if you just go on Google and you type in GPower here, can you see the screen? I think you can.
Yes.
Okay, so if you go on Google and you just type in GPower, the first link is to the GPower website.
So what country is it in?
I have no idea what country it's in.
Mhm.
And then if you go down below there,
Germany.
sorry?
It's Germany. with
Oh,
the E.
Germany. Thank you. I would have not known. Yes, so if you go down below, you have the option to download it, whether it's for Windows or for Mac. The download, it's a version of 3.1.9.7 now. I think I have that version, but it's not much different. They've just added a few more statistical tests in there. And then there is also a very helpful guide, which is download GPower manual. So it gives you a reference to certain statistical tests and how to perform that in GPower. It's very helpful if you want to learn on your own time. It doesn't go over every statistical test. So I just wanted to, give that resource as well. And then this is how GPower looks when you open it. Okay. How do I remove this? All right. So this is how GPower looks. Over here, first and foremost, the most important thing in GPower for me is when I look at the test based off of the statistical test that we're interested in. So for example, if I'm running a correlation, I can, navigate to the correlation and regression bar. Or if I'm looking at the difference between means, then I can navigate towards the means, and then you have options of performing a 1 sample t-test, a 2 sample t-test. You have options for looking at matched pairs, so a pre and post test, looking at the difference between a pre and post test. There's options for running ANOVA and COVA, repeated measures analysis. So here you have, just if you're looking at between factor repeated measure, if you're looking at within factor repeated measure, and then if you're looking at within between interactions. And then there are some options of multivariate analysis, MANOVA. So you're looking at a multivariate, not just a one-way ANOVA, but you're looking at a multiple analysis, multiple dependent ANOVA. And then if you're looking to test for the difference in proportions, then you go on the proportions options. You look at from the difference from constant, or you're performing a sign test. The good aspect of GPower is that it also gives you the parametric and non-parametric test results, which are very helpful, because sometimes based off of the distribution of our data, we might not have a normal distribution, so we cannot assume a normal distribution, and we might have to use a non-parametric statistical test instead. And then you have a generic F binomial test or a F test. So in today's session, I will go over how to perform two-sample t-test, ANOVA, and ANOVA within between interaction, and then a basic regression analysis in GPower. Okay, so here's, let's say this is an example. For exercise 1, our hypothesis here is that the dietitian wants to compare two different diets, A and B, for diabetic patients. So there's a sample within diabetic patients with diet A and diabetic patients with diet B. Here we will go on, our test. We know that this is a two-sample t-test. We're looking to compare two samples here. So here we will go on tests. We'll navigate to means, and then we'll go on two independent groups, because this is not a matched pair. So it's not, the reason why we're performing a two independent groups, because we're comparing two samples. Now you see here, the test family is a t-test because you're looking to compare difference between two groups. The statistical test is you're looking to see the difference between the means in diet A patients and diet B patients. The type of power analyses here, and I'll just move it here so it's easier to look through right now. The type of power analysis is based off of what is given to us in exercise 1. So for example, exercise 1 is saying, calculate the sample size for a given statistical power of testing the difference in the effect between the two groups, diet A and diet B, with a two-sided alpha of 0.05 and 80% power. And then it gave us the information of the mean of diet A is equal to 5, mean of diet B is equal to 10, with a standard deviation within each group of 3. This information is given in this exercise, but sometimes we don't. So if you're looking from prior literature review and you see that this is similar to the type of research question you're working on, and you see that you can calculate the sample size based off of the two differences given from a prior literature review, then you can use their mean and standard deviations and use that information to calculate your sample size here, just like how this exercise is provided. However, sometimes that information is not provided. Sometimes it's not in table 1 provided in the literature review. Sometimes you already know the effect size. So if you over here hover through effect size D, which is Cohen's D is your effect size information criteria for the t-test. It gives you information of what is a small effect size, a medium effect size, and a large effect size. So a Cohen's D of 0.20 is considered to be a small significant difference. A Cohen's D of 0.50 is considered to be a medium effect significant difference between two samples. And a Cohen's D of 0.80 is considered to be a large significant difference between the two samples. And then you have your alpha error, which is your significance level, your power, and your allocation ratio. So allocation ratio is pretty much within the two samples, how are you distributing the two samples? So for example, here I'm saying that they're equally, patients are equally distributed in the sample. So my allocation ratio is 1. For this example, for this exercise, my alpha will be set to 0.05, my power will be set to 0.80, And then I am performing a two-tailed test. So I'm trying to see what that there could be a difference in, there's a difference between diet A and diet B, and it could go either way, either direction. It is not one direction. So I'm not saying that diet A is more, the average of diet A is greater than the average of diet B, or the average of diet B is greater than the average of diet A. I'm going in either direction, so I'm using a two-tailed test. And then this is the input parameter here. So for example, since we already have the information, you press the determine option, and then here is some of the information that you can provide if you have this information already to calculate your effect size. So for example, for our exercise, the mean of diet A was 5. So I incorporated mean group 1 as 5. And then the mean of group 2, which was diet B, was 10, with a standard deviation within each group of 3. So the standard deviation within each group was 3. I calculated the effect size. So our effect size was 1.666, which is pretty small because if you look here again, a small effect size is 0.20. So we show a small difference between diet A and diet B. And then here, your calculation of effect size is 1.667. You can calculate and transfer to main window. So it'll directly go into the main window of effect size. And then you can calculate here, press calculate, and you'll see that a total sample size of 14 is required to achieve 81.6% power with a significance level of 0.05 if the effect size is 1.666. And then one of the things that I really like here is that you can create an XY plot for a range of values, which allows you to provide more information on how the sample size changes over either power or effect size. So here, for example, we're plotting, we selected the option of XY plot for a range of values. And then we're displaying the values in the plot. We're plotting the sample size on the basis of power. We can also plot it on the basis of effect size. So I'll just make this a little bigger.
Can I just ask what's meant by effect size? If it's 0.5, does that mean that there's 50 percentage points between them, but they're not percentages? So
No,
one is 50% bigger than the other?
effect size is the relationship between, is the difference in the relationship between the two samples. So it's pretty much saying that the effect size is, there's like, if you said 0.50, you're saying that there's a medium level difference between the two samples that you're interested in.
But it's not this, you don't mean the mean group 1 versus mean group 2, 5 and 10. That's
No, it's not. It's calculated
difference you're talking
using
about.
that. Effect size is like the mean group 1 and 2 and the standard deviation is the formula used to calculate the samples, the effect size for this specific test. But an effect size of 0.50 pretty much says that the magnitude of the difference between these two groups is like 0.50. It's a medium magnitude.
But can you give an example of two numbers that are that different? Just so that I know what you mean, like whether you're talking about relative or percentage point or what?
So like, for example, I can say, like giving an example, I can say, like for example, if you're just looking at the average difference in mean right now, because here we have our standard deviation within each group similar, it's the same standard deviation, and you're looking to compare the difference in means. Here you see that there is there's a 5%, like a 5-level change between the difference in the means. Let's say you were looking at a sample of 100 and 200, and then we have like, or 10 or 20, let's say, and we have like a standard deviation, which is 5. Your effect size will change. So let's say 10, 10, 10, 20, and then a standard deviation of 5. Your effect size changes to like a level of 2. So there's a larger difference between these means of the two samples. I hope I- Was that helpful? I hope I wasn't able
I
to.
don't want to take up too much time, so. But if I'm gonna be putting in the effect sizes, I just want to know like how I'm gonna get that from the data that I have, like the preliminary data that I have.
From preliminary data, it's based off of whether you have any significant difference between two mean groups previously. You know, if you're looking to compare two differences in groups, if there's prior literature review that's been performed, then you can use that value to calculate your effect size, or if there's already effect size provided. So pretty much saying that we think that there is like there's a small difference between the two groups, or there's a medium difference between the two groups. That's how you'll be able to use that information to calculate your effect size.
Okay, we should move on.
And then, all right, so here you see the XY plot. The XY plot here, you see it's sample size is marked on power. So you'll see how your sample size changes on the basis of power. If you have a lower power, then you have a lower sample size. And then if you have a higher power, you're having a higher sample size. So as you see, as sample size increases, your power also increases. And then this is helpful because based off of your small effect size, you can see how your power is changing over your, or how your sample size is changing over power. Okay, so for our example, we have a sample size of, total sample size of 14 required within the two different groups. So there in group 1, you'll require 7 participants. In group 2, you'll require 7 participants. A full sample size of 14 will allow us to obtain 81% power with us showing a small difference between the two samples in the average mean. All right, the next exercise here is we're just looking to compare the systolic blood pressures in females or males, and we want to determine the power to detect a small, medium, and large effect size. So now here we're looking to compute power. The type of power analysis we will be running will be post hoc because we are looking to calculate power given that we already have information on the sample size and we already have information on the effect size. So for example, I've given this information. Let's say we have a sample size of 30 in each group. That's a total of 60. And then we have an effect size of 0.2. The power we need to have a sample size of 60, total 60, and an effect size of 0.2 to demonstrate a small difference between the two groups will be about, it's a large power. It's like 118% power. Large power, very good power. And then let's say, for example, and this is just, for example, let's say I have a total sample size of 50 and I have 25 in each group. And I'm looking to detect a moderate or medium difference between those two groups with an alpha of 0.05, two-tailed test. I will require a sample size, my power will be 41. So it's a small power. Power is changing. So if I look at the plot here,
Isn't that power better than 0.11?
so if you multiply it times 100, that 100% power is really good power. It's considered as good, like you're correctly able to detect the significance of your test. You have 100% power to detect the significance of your test. 41% power is not as good, so you'll have to probably increase your sample size to increase your power. So here, for example, because you have a 25 and you're looking to detect a medium moderate effect size, you have a small power. So you have only 41% power to detect significance in the difference between the means in the two groups. So this pretty much states that you might require to, enroll more participants in your study. So for example, if I was to just go back and look at, like with a sample size of 50. So with a sample size of 50, let's say, and I say 80% power, how much effect size would I have? I would have a very small effect size. So my sample size is very small to detect, you know, and it detects only a small difference with 80% power. It's showing only a small significant difference between my group A and group B. And so and I have like 80% power that it can detect a small significant difference. But I need, if I want to have a medium, like if I want to see more of a difference between my two groups, I will have to increase the sample size. And then here, so for example, so the answers are here below. So I did this for 30, I gave an example of 60, but like, let's say the sample size was 30, 15 in each group with an effect size of 0.20, your power was 82.6%. Because you were showing a small significant difference. So it was good. It was with a sample size of 30, you had a good power to detect a small significant difference between the two groups. With a sample size of 50 and showing a medium significant difference between the two groups, you'll have a very small power to detect that significance. So like 41% is not really good. If you have a large sample size of 100 and you're looking to detect a large significant difference, then you have really good power, which is 97.7%. So it's pretty much, as your sample size is increasing, your power also increases. And it depends on your effect size of whether it's able to detect a small, medium, or large difference. And then when we're interpreting the sample size calculation results, so for example, here, if I was to interpret this result, let's say, let me just give an example. So let's say I'm looking for a 50 effect size difference and I'm calculating sample size with a power of 80. I would require, so my interpretation would be with 128 subjects, or no, sorry, with 64 subjects per group, 128 total subjects, we will have 80% power to detect a medium Cohen's d effect size of 0.50 based on a two-sided level of alpha significance level 0.05. And then like we can mention that preliminary data or similar studies with, you know, X amount of subjects per group showed this a medium effect size. This is how we would interpret our sample size calculation results. Now, moving forward, the non-parametric Wilcoxon-Rank Sum test, it's also known as the Mann-Whitney test. It is the non-parametric version of a independent sample t-test. So the independent sample t-test was a parametric version of the test when it assumes normal distribution, where the data tends to be, you know, spread around a central value with no bias towards left or right of the mean. So it's, you know, spread equally, and it's showing a bell-shaped curve in your model. However, the non-parametric test, it assumes no normal distribution, and it assumes that it doesn't assume any shape or the shape of the parameters or the distribution of the parameters. And so if you don't have that information on you, you can run a non-parametric Wilcoxon-Rank Sum test based off of, you know, your outcome of interest. So there's a few options here. Let me see. So if you go on means, you can go to the two independent groups Wilcoxon non-parametric test, which is comparing two samples. So similar to t-test, but a non-parametric version. It's comparing two samples where you're comparing to look at the difference between the two groups, but you're not assuming that they're normally distributed. And then here, there's some information. So whether it's a one-tailed test you're interested in or a two-tailed test, the parent distribution. So there's a few options in parent distribution. So parent distribution normal pretty much assumes that there's normal distribution. And then the parent distribution Laplace, it's the distribution between the two independent variables with identical exponential distributions. So if they're exponentially distributed, it's usually used to model the data that have like heavy peaks or heavy tails in their distribution. And then the logistic distribution is, for example, here, the logistic distribution is used to describe the model growth. So it's pretty much a symmetrical distribution and has like one peak in the distribution. This can be seen when you run like a histogram or a univariate analysis and looking at how the data is distributed for the sample, and you can assess whether it's normally distributed, whether you want to use a function of Laplace, logistic, or min-R. Min-R is pretty much like asymptomatic relative efficiency. It's defined to power the two group t-tests, and it's usually the most conservative one. So usually you tend to use min-R because it provides us with a larger sample size, and it gives us more information on the sample size. So that's the most used one, unless we're assuming for like normal distribution. So I'm going to, for this example, keep min-R as one because it provides us with like the most conservative result, provides us with a larger sample size estimate. Okay, and then here you still have the effect size, Cohen's d, because it's a t-test, and then you have your significance level information, you have your power, and then you have your allocation ratio. So how are the two groups are they equally balanced? Are there equal amounts of data in the two groups, equal amount of participants in the two groups? So that's that information. So let's say, for example, we have a stomach cancer study, and the hypothesis is to define genes that regulate gastric cancer metastasis to the liver across the two groups of mice. So we're pretty much interested in seeing whether there was a difference between the median, let's just say hypothetically, gene regulation, difference between the two groups. So whether there's a difference in group 1 median of mice comparison to the group 2 median of the group 2 in mice. So our alternative hypothesis is that there will be no difference. The median of group 1 and median of group 2 mice are equal. And then our alternative hypothesis is that since it is a two-tailed test, it is that there will be some kind of difference. There will be a significant difference, or there is a difference between the medians in the two groups. So here the question is, what is the sample size needed to detect a difference in the medians between two mice groups? Two mice groups, two-sided, our significance level is 0.05. We've given 80% power and an effect size of 0.49. So if we're looking to calculate the sample size, we have given alpha, we have our power, and we have our effect size already given to us. I use the parent distribution of min-R because it provides us with the most conservative results. And then for effect size, since I already gave the effect size information, I use 0.49 here. However, you can also calculate your effect size based off of the prior literature review information. So if you already have information on the mean and group, so if there's like a previous paper that has been published and they've provided with the mean and standard deviations of mice in group 1 and mice in group 2, you can use that reference to calculate your effect size and then calculate your power analysis based off of your study research question of interest. So our effect size here given is 0.49, which is pretty much almost a medium effect size, because if you know 0.2, I don't know, it's not hovering here. 0.2 is a small effect size, 0.5 is a medium effect size, 0.8 is a large effect size. So if I calculate that, I see that I need 77 subjects in each group. So in each mice group, I need 77 individuals, a total of 154 individuals at 80% power to obtain a almost medium effect size. So medium effect size, let's just say, because it's estimated to 0.50. So to see a medium significant difference between the median gene regulation numbers, you'd like to enroll 154 subjects, 77 in each group to have an 80% power, and to show an medium effect size. The next question here was to determine the power to detect a small, medium, and large effect size with a two-sided Mann-Whitney test for placebo and new drug treatment sample sizes of 5, 8, 10, and at alpha 0.05. So we're running a two-sided tail test again, and here we don't have the effect size information. We are calculating the effect size, so we will perform a sensitivity analysis here. And we have information on the power, which is 80%, but you can also increase the power to 90% if you want a higher power, and like if you want to be able to detect more of the relationship between the two difference in the two groups. And then your sample size here. So let's say your sample size for group 1 is 5 and your sample size for group 2 is 5. You will need a 2.24 effect size, which is a very large effect size, pretty much. And then if you look here, let's say our sample size group 1 is 8, sample size group 2 is 8, you see that your effect size decreases. So as your sample size is increasing here, your effect size is decreasing. It's moving down. It's so I'll show you with the XY plot for range of values. So plot on okay. So here, if you see here for this Mann-Whitney U test, if you have a smaller sample size, you'll have a higher effect size. So because you have small subjects of data, there's pretty much saying that you see larger difference because it's so constricted and you have like small amount of data samples in your data. When your sample size increases and it keeps increasing, your effect size will become smaller here because it's pretty much saying that there is a smaller difference as your sample size is increasing. There will be a smaller difference between the two mice groups. This is using the parent distribution, which was like the most conservative one. So it can change based off of what kind of parent distribution you're using. And mind you, this is a non-parametric test that we're running, so it will be different from the results that we obtained from a parametric assumption test. So for example, if we ran So for example, if we assume normal distribution for the parent and we had a larger effect size, we'll have a smaller sample size. And then as your sample size is increasing, your effect size is decreasing. You'll see that because you have a larger sample size, you have more variability in your data. And so there will be a smaller difference that can be seen because of the more variability in your data. And these are the values to detect a small, medium, or to detect a sample effect size based off of 5 sample or 8 or 10 per group. All right, the next example is a paired sample t-test. So we perform a paired sample t-test when we are looking to see whether there's a difference between means pre and post of a study. So for example, if you were looking at to compare the means of BMI in participants pre an intervention and post an intervention, you will run a paired sample t-test. Here, there's an example of a paired sample t-test, which is a weight loss program study. A company markets an 8-week-long weight loss program and claims that at the end of the program, participants will lose, on average, 5 pounds. So they're claiming that on average, they will lose 5 pounds. The research goal is to validate whether there was any weight lost after following the 8-week-long weight loss program. So here you have conducted, you've calculated or observed individuals' weight pre the intervention, and then you have observed their weight post-intervention. The mean difference between the post-intervention and pre-intervention is 5 pounds with a standard deviation of 5 pounds. So this is an assumption, this is what the hypothesis is, that the mean difference between the pre and post-intervention would be 5 pounds, and their standard deviation is 5 pounds. Now, when we're running this in GPower, we go test, we go on means, and we go for 2 dependent groups matched pairs, because this is a pre and post test that we're running. So these are two dependent groups matched pairs. They're dependent on each other. One, it's 2 groups, but we're looking at the same participant pre and post. When you go on the means difference between 2 dependent means, you're looking at the difference between the 2 dependent means pre and post. And for this example, or for this exercise, you're calculating the sample size needed for a study using a paired t-test with a significance level of alpha 0.05 and 90% power. So here, my alpha is 0.05, my power will be 0.90. I'm running a two-tailed test, so I'm pretty much saying that there is the mean difference between the post and pre-intervention is 5 pounds, is not 5 pounds, or it is 5 pounds. So there is no difference between the pre and post intervention, and there is a difference between the pre and post intervention. So from differences here between between pre and post, as I provided, the difference between the post intervention and pre-intervention will be 5 pounds, and their standard deviation was 5 pounds. You calculate the effect size, which was 1, pretty large effect size, and then you calculate the sample size after that, after transferring that, with a power of 90%. So here, you need total sample size of 13 individuals to see a very large effect size with a power of 90% in your study. And then if we said, let's say we say that we want to look at the difference, but we're trying to see whether there was a medium or a moderate difference between the pre and post test results of your intervention. So I say 0.50, I will require a sample size of 44 individuals in the 2 groups. So total sample size of 44 individuals, 22 in each, like total sample size 44 individuals that will have a pre and post result of their intervention weight loss information. And then here you can see as your power, or let me show you not in the basis of power, but how effect size will change. So at 90% power, when your sample size is pretty large, you have like above 1,000, you have a smaller effect size, you have a smaller effect size. And then as your sample size reduces, your effect size is also reducing here, because they're showing that, or your effect size increases here because there's more showing to be more variability in the difference in your between the 2 groups. So for our answer, we had a total sample size of 13 based off of the mean difference between the post-intervention and pre-intervention to be 5 pounds with a standard deviation of 5 pounds. And then another example, let's say we are performing a cholesterol study and we want to investigate the levels of cholesterol in men in group A study that changed over 6 months from baseline. So our null hypothesis was that there is no average difference in cholesterol from baseline to 6 months. You'll see that there's no difference. So it's just saying that the null hypothesis, the difference is equal to 0. And then the alternative hypothesis is that there is an average difference in cholesterol from baseline to 6 months. So in men in group A, the pre-intervention, the level of cholesterol did change over after assessing it post in 6 months at 6 months time point. Here the question is, how many subjects are needed to detect a small, medium, and large effect size with a two-sided test at alpha is equal to 0.05 and 80% power? So we have 80% power. Let's say we have a small difference. So we're pretty much saying that there was a small difference observed in the average cholesterol levels in the participants who were in this study. Their cholesterol levels changed not like changed small, or there was a small difference between their post and pre average cholesterol levels. And then here I'll change this to 80% power. Our sample size is 199. So we need about 200 participants in our study to observe a small effect size. And if we want to look at a medium effect size difference between the men in pre and post the 6 month baseline group, you'll need a total sample size of 34. So you see how like your effect size is increasing, your sample size all of a sudden reduces, because now you have smaller sample size, so it's more constricted, and you are, you can see that there's a much larger difference between the average cholesterol levels. And then for 0.80 effect size, which is a large effect size, you'll see that your sample size decreased again. So a smaller sample size and your effect size increased. And these are the answers here. So you see, with a small effect size, we needed a large sample size of information to detect small significant difference between their pre and post results. And as you go over, as your effect size increases, your sample size is reducing. You don't need that many participants to detect a medium or a large effect in your between your pre and post test results. Now, moving forward, we're performing a one-way ANOVA. Why do we perform a one-way ANOVA? It's when we're looking to test for this difference in means between two groups or more. So, for example, here, it's a Carter burden study. We want to identify whether there was a difference in the mean systolic blood pressure among the 4 BMI groups. So there's 4 BMI groups. It's a factor level. They're divided up into 4 different levels: underweight, normal weight, overweight, and obese. And we want to compare the difference in the mean systolic blood pressure across these 4 groups. So our null hypothesis is pretty much stating that there's no difference in the mean systolic blood pressure between these 4 groups. So individuals that had the average systolic blood pressure in underweight group is equal to the average systolic blood pressure in normal weight group, in overweight group, and in obese. Whereas our alternate hypothesis is stating that there is a difference between one of the means, or maybe more than one of the means, in systolic blood pressure among the 4 BMI groups. So means are not all equal. So it could be either 1, 2, or maybe all of the means are not equal. So our question here is, what is the minimum effect size that can be detected with 12 subjects per BMI group using alpha at a significance level of 0.05 and 80% power. So here you go to means again, and you have a lot of options here. So many groups and COVA, when you're looking at ANOVA, or you also have covariate informations, you can use this option. If you're just performing a one-way ANOVA, which is the exercise right now, you use many groups ANOVA one way, so one independent variable, because our outcome of interest is the systolic blood pressure, and our independent variable is the group, which is underweight, normal, overweight, and obese. And then if you have many groups, so whether you're looking at more than 2 factors, which will be the next example, then you'll use the main effects and interaction group. I'll show you that after the one-way ANOVA. So let's perform many groups ANOVA one way with one independent variable. And here you have, now we move to the F test. So the T test is pretty much, we're using to compare the difference in between means in a sample. And then the F test is used when you're looking to compare the difference in the variance. Okay. All right, so here, since we are required to perform we want to see the minimum effect size, we will perform a sensitivity analysis where we have the alpha given, we have the power, and we have sample size. So we have 12 subjects per group. We have 12 subjects per group. Now, how many groups do we have here? That depends, because we have 4 BMI groups. So 4 BMI groups, let me write that. We have 4 BMI groups. And then we have a total sample size of 12 times 4, which is 48. Is that 12 times 4 is 48, right? Yeah. And then number of groups is 4. And our power is 80% power. You can calculate that. So here you see, when you're calculating the effect size, you have to provide the total sample size, estimated sample size also, if you have an estimate of how many participants you're planning to enroll in your study. You can say, like, let's say you have an estimate that you can only include 200 participants in your study, and you want to see what's the effect size. Then you would put, instead in total sample size, you would put 200. Here I'm saying that can be detected with 12 subjects per BMI group. So in the 4 BMI groups, I included 12 individuals. So there's total sample size is 48. And the number of groups here are 4. I calculate the effect size, which is 0.49. Now, if you go back here, this chart kind of gives you an idea of like what is a small, medium, or large effect sizes. So Cohen's F here, before we were looking at Cohen's D, which was looking at the T tests. Now we're looking at the F tests. So we will be following the Cohen's F effect size, which is the small effect size is 0.10, medium effect size is 0.25, and a large effect size is 0.40 and above. So here, we calculate is this working? Hi, can you guys see the screen still?
Yep.
Okay, I thought it was my computer's freezing, sorry. It's just not moving as much. Okay. So, right. So here we'll see that we have an effect size of 0.49, which is a pretty medium to large effect size here, based off of Cohen's F. Pretty large because 0.10 was small effect size, 0.25 was a moderate effect size, so 0.40 and above is a large effect size which pretty much means that we see that the difference in the average BMI, systolic blood pressures among the 4 groups is large. There's a large difference in the average BMI systolic blood pressure groups. And then here we are performing a two-way analysis of variance. So if it's not a one independent variable, now you have 2 variables of interest. You're looking to see, for example, you want to investigate the roles of a Fanconi anemia pathway outside of an FA test, outside of FA. So you're testing to see whether there is an interaction between genotype as a 4-level factor and stress condition as a 2-level factor. So here, your null hypothesis is pretty much stating that there is no interaction between genotype and stress condition. And your alternative hypothesis is there is an interaction between genotype and stress condition. In this example, am interested in the interaction, but I'll also show you based off of each predictor variable. So based off of each factor variable, how can we calculate the effect size? So we go to tests, we go to means, and we perform many groups, main effects and interactions, 2 or more independent variables. Okay, so here, yeah, so you have your alpha. What is the minimum effect size that can be detected for sample size 6, 10, 12 mice per group using a 0.05 significance level and 80% power? So here my power is 80%. My alpha significance level is the same. My numerator and number of groups are the 2 new methods that I need to calculate. So since we have 2 factors here, one is a 4-level factor and one is a 2-level factor, our numerator is found by taking the number of the levels for the predictor minus 1. So, or for example, let's say that we are interested in just looking at genotype. It's a 4-level factor, so our numerator will be 4 minus 1, 3 degree of freedom. Or if we were just looking at stress, then our numerator would be 2 minus 1. Degree of freedom would be just 1. Here, if I'm looking at the interaction, which is 4 minus 1 times 2 minus 1, that will be the numerator degree of freedom. So 4 minus 1 is 3, and 2 minus 1 is 1. So my numerator degree of freedom would be 3. And then the number of groups are pretty much, how many groups will there be? So there will be 8 groups, 4 times 2, because we have a factor with 4 levels and a factor with 2 levels. So there'll be 8 groups here in our study. And if we're computing the samples, we're computing the effect size. So we're performing a sensitivity analysis. So let's say we have six groups, 6 times 8, 48. So 48 is our total sample size. Our numerator, we're looking at the interaction. We're focused on whether our hypothesis is talking about there's no interaction or there is an interaction, alternative hypothesis. So since we're focused on the interaction, our numerator degree of freedom would be 3, and our number of groups is 8. Our sample size, our effect size would be 0.50, which is showing that there will be a large difference. There's a large effect size in showing the interaction between genotype and stress condition. And then for a sample size n per group, 10 in each group, so 80, 10 times 8, because there's 8 groups, our effect size will go down. It'll be a 0.379 effect size. So we have a moderate variability in amongst the genotype and stress or our outcome of interest levels between those 2 groups. And then as you go more forward, you have, so I'll just give you the results because we're running out of time. So if you go here and per group 12, you'll see that your effect size decreases, it goes down because you have a larger sample size now and your effect size is smaller 0.25 to 0.40 is pretty much like it's a medium effect size, showing based off of the age groups. So if you have 12 individuals in each, or 12 mice, or according to the study, if you have 12 mice in the group, in each age group, then you will be able to see a minimum effect size, a medium effect size interaction between the genotype and stress conditions. Okay, and then lastly, the last example I have is multiple regression. So here you can perform regression using the correlation and regression tab. There's multiple regression options, like a linear bivariate regression. You're just looking at one group, seeing the size of the slope. You're comparing to see whether there's a difference between the intercepts in two groups, performing a bivariate regression, or you're looking to compare the difference between the slopes. And if you have a linear multiple regression, so with this, it's a fixed model. You're looking to see whether the deviation in the R square changes. R square is pretty much the variance in the variance. It explains the variance in the model. So R square pretty much says that our model, let's say, has specific variables of interest, and if we have 40% R square, like if our R square is 40%, it says that 40% of the variability in our model is explained by the specific predictors that are available in that model. And then linear multiple regression fixed model R square increase. So the R square increase, it shows how the R square changes. And then you're just looking at a linear multiple regression model, fixed model, single regression coefficient. So you're looking to look at the regression coefficient of one specific estimate. And then you have logistic regression and Poisson regression. So here I will be interested in R square increase because I'm looking to see whether there was a change in adding a specific predictor variable into your model or not. So I went to linear multiple regression fixed model R square increase. Now here our question is, we're looking at the effect of gender, family income, mother's education, and language spoken on the at home on the English language proficiency scores of Hispanic high school students. The variables here that I'm considering as control variables are gender and family. So gender and family income are considered as control variables, and then they're not of primary interest. Mother's education was a continuous variable, and the home language 1 and 2 are categorized. So they're factor variables, which are categorized into either Spanish only, both Spanish and English only. So from previous researchers, we believe that, the R square for the full 5 models, for the full model with 5 predictors, with these 5 predictors, 2 controls and 1 continuous research, and 2 dummy variables for the categorical variable will be about 0.48. And we think that our beta 3 mother's education will add about 0.03 to the R square of our model when it is added last into our model. So, okay, my laptop is slow. Sorry. So I just showed here, I just showed in the screen here instead to make it easier. But here I included for the number of tested predictors that we were looking at, it was mom education. Can you see this, or is it too small? It's probably too small. Okay.
That's not better.
Yeah. So here, the number of tested predictors that we're testing was mom education. We were just focused on mom education, and the total number of predictors that we had in our model were 5. And here, from variances from previously, we had a 0.0 so let's say we had, let me just go back and backtrack. Okay. So for example, from 0.048, so we had our variance of, let's say we have a effect size of 0.048, and we're looking at our 2 predictors, or 2 predictors of interest, let's say home lang and home language 1. So we will add the number of tested predictors as 2 and the total number of predictors in our model as 5. And our effect size was 0.048. So we require a total sample size of 199 subjects. If we had a full model with 5 predictors and 2 main predictors that we're focused on, showing a 0.048 effect size. This effect size was given previously based on prior information. However, you can also calculate the effect size. So if you look at the determined table, these are the options. So from variances, variance explained by special effects. So let's say that we say by adding 2 dummy variables into our model, we are seeing that we will see an increase in the variance by 0.025. So then and the residual variance will become 0.5 to 1 minus 0.48. So how much is 1 minus 0.48? 0.52. That will help us calculate the effect size, which was 0.048. And then now we can see that if we're looking to test for 2 predictors and we have a model with the 5 predictors, then we have an effect size of 0.048, which gives us a sample size of 199. So the residual variance is pretty much defined by the previous information that was already given, which was 1 minus 0.48. So we see that we had still 0.52 as a residual variance. And now that we're focused on looking at 2 predictors, instead of looking at 1 predictor, we added 2 predictor here, and we see how the variance changes by adding those 2 dummy variables into our model. All right, and then lastly, we show the power for a variety of sample sizes and difference in the means in the table so that grant reviewers can see the power significant to detect a range of differences. So that's if you're running a power analysis in terms of correlation, in terms of regression, or in terms of looking at the difference between means or proportions, it's highly beneficial if you provide some range, unless you do have a knowledge and information on like whether you're actually looking for a small difference between means, or you're looking at the strength of relationship, which is pretty moderate, or your coefficient is exactly you're looking to estimate a coefficient of exact the same amount. But usually for grant applications, it's best to provide over a few ranges of differences with expected sample size. And to provide the sample size calculation, you can use preliminary data. So if you already collected data, you can use that information to like preliminary data to calculate your sample size based off of it. Or you can also use prior literature review as some knowledge. However, if you don't have any of that information, it's based off of clinical relevance. So if you think that there's a significant difference between 2 groups, which is pretty large, then you can show that I assume that with this effect size, a large significant difference between the 2 groups, I will have this much sample size. Or if you're looking to have like a small relationship between 2 variables of interest, correlation, then you can provide that information, sample size calculation. And then you also adjust for dropout rates. So let's say if you have dropout rates in there, you have 20% dropout rates. So you increase your sample size by like 10 or 20%. But yeah, if you have any questions, feel free to email me. I can provide the slide and the PowerPoint, the recording for your reference if you would like to go backtrack. Thank you.
Thank you very much. Thank you. It was great.
Thank you.
Appreciate it.
Thank you.